Okay, so either way we do this is going to require us to translate this system of equations into a matrix. And that matrix is just going to be the variables and then the augmentation with the constants. To put it in a matrix, we first have to have the system organized in a certain way. This system already is, but let's point it out. We have to have a first column here that is all of the x values. That's what we have here, all the x values. Then we have to have a second column that's all of the y values, and that's what we have right there. Then we have to have all the z values together, and we do. We have to have the equal sign lined up here, which is for this system, and then the constants, which we have over there all on the right side of the equal sign. So the system is set up and lined up in such a way that we can translate it into a matrix real quickly. So that first equation is going to give us a row of 2, -4. That's just a z, so we think of that as a coefficient of 1. Then it's augmented with the constant of 3. The second equation gives us x, -3, 1, and then augmented with 5. And the third equation gives us a row of 3, -7, 2, and 12. Now, for Gaussian elimination, what we would need to do, put just x, so that should have been a 1, not an x, sorry. For Gaussian elimination, what I need to do two things. I need to make all of these equal 0. Those three there, they're to the lower left side of the diagonal. Those have to be 0. The numbers on the diagonal here have to become 1. Everything else in the matrix doesn't matter. That's for Gaussian elimination with back substitution. If I want to use Gaussian Jordan elimination, I have to go a step further. I have to make these entries to the upper right side of the diagonal also 0. Notice that neither one of them has any specifications for the augmentation. The augmented values take on whatever they take on as we do our operations with the matrix. I have found that it's generally just as easy, if not easier, to do Gaussian Jordan elimination as it is to do just Gaussian elimination with back substitution, because it allows you to start eliminating in any column. So I'm going to go ahead and do Gaussian Jordan elimination, which means I need to eliminate everything on either side of the diagonal and make them equal 0s. Now, it doesn't mean I have to keep the equations in their same position. It might be easier to move them around. So let's go ahead and take a look. The only variable I see right now that's really easy to get rid of is in the first 2 lines there, that third column. Both has 1s in it. So I'm going to take this top row and I'm going to multiply it by -1. That'll give me a -2, +4, -1, and 3, or -3. The other rows I'm going to keep as they are. And then I'm going to, my brackets on that. Then I'm going to combine those first 2 rows, add them together, and replace the second row with them. Now for the top row, I'm going to go back to what I had originally up here. 2, -4, 1, and 3. For the second row, I'm going to combine them over here. So I got -2 and 1 makes -1. 4 and -3 makes +1. -1 and +1 makes 0. -3 and 5 makes +2. Then the bottom row isn't going to change. So this has accomplished a couple of things for me. It's given me a 0 in this third column, and it gave me a 1 in that second column. So that could be used now as the that second row. I've got a 1 in that right spot. Well, I need to eliminate, since I got rid of that third item in the second row. It'd be nice if I can get rid of the third item in one of the other rows as well. That way, when I go to do some elimination, I have a set that already has zeros in the same spot. So I'm going to take the top row again, and I'm going to use it to eliminate that 2, the third item in the third row. So I'm going to multiply that top row times a -2 now. I'll bring it over here. So that makes this -4, +8, -2, and -6. The middle row we're not doing anything with right now. And the bottom row, we're going to leave the same. We're going to combine that here in just a second. So I'm going to combine this new first row and the bottom row. I'm going to replace the bottom row with it. So for the top row, I'm going to go back to what I had before I multiplied it. The 2, -4, 1, and 3. The middle row I'm not touching. The bottom row is going to become, I have -4 and 3 makes -1. I have 8 and -7 makes 1. -2 and 2 makes 0. And -6 and 12 makes 6. At this point, I see an issue. These two rows, the second and third row, have the same elements in the first 3 columns. The augmentation is different, but they have the same elements in these 3 main columns. When that occurs, remember that means that this is either going to be inconsistent or dependent. Dependent means that 2 of the equations are really the same equation. Inconsistent means they're parallel, so they can never have a solution. How do I know? Well, if the augmentation were the same, that would mean it was dependent. Here, however, the augmentation is different. That means it is inconsistent. So there is no solution to this system of equations. If I want to try to put it in the calculator, do that matrix edit. This is going to be a 3 by 4 matrix. If I wanted to put in the elements of that original matrix, I've got 2, -4, 1, and 3. I've got 1, -3, 1, and 5. 3, -7, 2, and 12. I go back and do my matrix calculations, my math. I'm looking for RREF, reduced row echelon form. And I go matrix, select matrix A. And you see it will not reduce it to row echelon form. It doesn't give me zeros in those columns. So in reduced row echelon form, I should have 1s down the diagonal and 0s everywhere else except for that third column. So it's telling me that this one does not solve. It doesn't work out. So there is no solution for this system of equations. There's no values for x, y, and z that'll make all 3 equations true at the same time. Okay, I realize that wasn't the nicest way to start out our class today. But we are going to continue on today with more about matrices. And we're going to talk about operations with matrices. We're going to talk about addition and subtraction first. For addition and subtraction to occur with matrices, the matrices being combined must have the same dimensions. To equate matrices, for two matrices to be equal, they also must have the same dimensions. Remember, the dimensions are the number of rows by the number of columns. This matrix here has 2 rows and 4 columns. That is a 2 by 4 matrix. If I have two matrices to be equal, that means corresponding elements must be equal. So let's take a look. Let's create a matrix here. So this is a 3 by 2 matrix. This element right here is considered element 2, row 2, column 2. It's element 2, comma 2 if you want to find its location. For that to be equated to another matrix, like this, every element has to be equivalent. So I can actually use this to match up equations. 2 has to equal 2x minus 8. 3 has to equal x minus 2. 4 has to equal 2x minus 6. Negative 1 has to equal x minus 6. 0 has to equal 3x minus 15. And 5 has to equal x. Well, I set this one up rather simply. We've got 5 equals x is actually one of these pairs of elements. So we know that x is 5. By substituting x into each of these, 2x minus 8 is 2, x minus 2 is 3, 2x minus 6 is 4, x minus 6 is negative 1, and 3x minus 15 is 0. You see that the elements are equivalent at each location. Well, let's look at one that may be just a touch more complicated than that. We might have x plus 2, 3y minus 1, y, and 5z. If I say that's equivalent to negative 3, 11, 4, and 10, we get a system of equations. I know that x plus 2 has to equal negative 3. I know that 3y minus 1 has to equal 11. I know that y has to equal 4. and that 5z has to equal 10. Now this is not a complex system of equations because each equation can be solved on its own. First of all, y equals 4. If I test that up here, 3 times 4 is 12 minus 1 is 11. So y equals 4 works for that element as well. X plus 2 equals negative 3. If I subtract 2, gives me x equals negative 5. 5z equals 10. If I divide by 5, I get z equals 2. So I've solved my system of equations. It's produced by those two equal matrices. So let's add or subtract our matrices here. Let's take this matrix minus this one. To subtract two matrices. These are both the same dimension. They're 3 by 2. That is a requirement. We combine the corresponding elements. So the elements in row 1 and column 1 get combined to make the element in row 1 and column 1 of our solution. We're subtracting, so we subtract the elements. 3 minus 5 gives us negative 2. Row 1, column 2, we have 8 minus a negative 3 is a positive 11. Row 2, column 1, we have 7 minus 2 gives us 5. Row 2, column 2, we have 5 minus 7 is a negative 2. Moving down to row 3. Row 3, column 1, we have negative 2 minus 0. That's just negative 2. And row 3, column 2, we have 0 minus a negative 4, which is positive 4. So that is the difference of those two matrices. Subtracted the matrices. Now you can see from this that addition is about just as simple. Both of these matrices are 2 by 4 matrices, 2 rows and 4 columns. We're adding them, so again, we combine the corresponding elements. 3 and 6 make 9. 3 plus 6 is 9. Row 1, column 2, 8 plus negative 4 is 4. Row 1, column 3, 9 plus 2 is 11. And row 1, column 4, negative 3 plus 1 is negative 2. Down to row 2, column 1, 4 plus negative 3 is 1. Negative 5 plus positive 5 is 0. Column 3, 7 plus 2 is 9. And column 4, 1 plus 0 is 1. So that's pretty simple. When it comes to matrices, there's two types of multiplication. The first type of multiplication we're going to discuss is scalar multiplication. Scalar multiplication is found by multiplying the whole matrix by a single number. And all that does is multiplies every element of that matrix by that number. For example, let's have 3, 7, negative 2, 0, 5, and 1 is our matrix. And we're going to multiply that matrix by 6. Multiplying the matrix by 6, that makes this a scalar multiplication. The scalar is the 6. It's multiplying. We just simply multiply each element in the matrix by 6. So it doesn't change the dimensions. The 2 by 3 matrix is going to stay a 2 by 3 matrix. 6 times 3 is 18. 6 times 7 is 42. And 6 times -2 is a -12. That's the first row. The second row, 6 times 0 is 0. 6 times 5 is 30 in the second column. And finally, row 2, column 3, 6 times 1 is just 6. So that's scalar multiplication. We could multiply, scalar division isn't really a thing because we can just multiply by a fraction is the same as doing scalar division. Matrix multiplication is much more complex. From the first matrix, we take the row elements times from the second matrix, we take the column elements. What does this mean? Well, it means let's just look at a very simple matrix multiplication here. Like this. Now these are both what we call square matrices. They're 2 by 2. The rows equal the number of columns. If we have square matrices, they have to be the same size in order to multiply. A requirement for matrix multiplication, by the way, is your first matrix has dimensions R1 by C1. Your second matrix has dimensions R2 by C2. For matrix multiplication to work, the number of columns in the first matrix has to be equal to the number of rows in the second matrix. Well, these are both 2 by 2, so it's going to equal no matter what. In our resulting matrix, the dimensions of the resulting matrix are going to be the number of rows in the first matrix by the number of columns in the second matrix. Again, these are both 2 by 2, so our resulting matrix is going to be 2 by 2. Now I put a rather large set of brackets out here just to give us some space, because there's some calculations that are going to go on inside here. So this is row 1, column 1 here. To find the entry in that location of the resulting matrix, we take row 1 from the first matrix. Remember, we take the row from the first matrix. And column 1 from the second matrix. We take the column from the second matrix. And we multiply the elements in order. So the first entry of row 1 is 3. The first entry of column 1 is 5. So that's going to be 3 times 5. And to that, we're going to add the second element of this row of 4 times the second element of that column of 3. So 4 times 3. For row 1, column 2, I'm still looking at row 1 over here, but now I'm looking at column 2 in the second matrix. So the first element of each is 3 times -1, plus the second element of each will be 4 times 0. Moving down here, this is row 2, column 1. So I'm looking at row 2, column 1. I get the first entry of each, I have -2 by 5. So -2 times 5, plus the second entry in each, 5 times 3. And finally, for the last entry here, this will be row 2 and column 2. I use still row 2 of the first matrix. I'm going to use column 2 of the second matrix. So row 2 is -2 times -1 are the first elements, plus second elements is 5 times 0. So the resulting matrix in row 1, column 1, 3 times 5 is 15, plus 4 times 3 is 12. 15 plus 12 is 27. In row 1, column 2, 3 times -1 is -3. 4 times 0 is 0. So -3 plus 0 is -3. Row 2, column 1, -2 times 5 is -10. Plus 5 times 3 is 15. -10 plus 15 is 5. And in row 2, column 2, -2 times -1 is 2. 5 times 0 is 0, so 2 plus 0 is 2. There's the resulting matrix from that multiplication. Now again, that one was the same size as the original matrix, or the original matrices, because they were square matrices. If they're not square, it could turn out to be slightly different. Let me show you what I mean. So let's do this 2 by 3 matrix times so this 3 by 2 matrix times this 2 by 3 matrix. This is 3 by 2. This one here is 2 by 3. Remember, these inside dimensions have to be equal. And they are. The columns of the first dimension equals the rows of the second matrix. My resulting matrix is going to be 3 by 3. The leftover, the rows of the first and the columns of the second. So this element right here, row 1, column 1, is going to use row 1 of the first matrix, column 1 of the second matrix. So that'll be 5 times 4 plus 3 times -1. 5 times 4 is 20. 3 times -1 is -3, so that is a 17. The second element This is row 1, column 2. So I still have row 1 from the first matrix. I'm using column 2 from the second matrix. So I take the first element, 5 times negative 3, plus the second element's 3 times 5. Well, 5 times negative 3 is negative 15. 3 times 5 is positive 15. Negative 15 plus 5, positive 15 is 0. My third element there is row 1, column 3. We're still taking row 1 from the first. Now we're using column 3 from the second. The first element's 5 times 2, plus the second element's 3 times negative 2. 5 times 2 is 10. 3 times negative 2 is negative 6. 10 and negative 6 make 4. Moving down to the next row. So this is now row 2, column 1. So we're going to use row 2 out of the first matrix, column 1 out of the second matrix. Our first elements are negative 2 times 4. Second elements are 0 times negative 1. Negative 2 times 4 is negative 8. 0 times negative 1 is 0. So negative 8 plus 0 is just negative 8 there. Next position is row 2, column 2. So we're still using row 2 out of the first matrix, but we're using column 2 out of the second one. So first element's negative 2 times negative 3, plus the second element, 0 times 5. Negative 2 times negative 3 is a positive 6. 0 times 5 is 0. So 6 plus 0 is 6. The next place is row 2, column 3. So we're still using row 2 in the first matrix, using column 3 in the second. The first element's negative 2 times 2, plus the second element is 0 times negative 2. Well, negative 2 times 2 is a negative 4. 0 times negative 2 is 0. So negative 4 plus 0 is just negative 4. Our next element there is row 3, column 1. So we're moving down to row 3 of that first matrix and column 1 of the second. So the first elements, we have 3 times 4, plus the second element is negative 1 times negative 1. Well, 3 times 4 is 12. Negative 1 times negative 1 is 1. 12 plus 1 is 13. Our next element's row 3, column 2. So we're still using row 3 of the first matrix, moving over to column 2 of the second. First element's 3 times negative 3, plus the second element's negative 1 times 5. Oops, negative 1 times 5. 3 times negative 3 is negative 9. Negative 1 times 5 is negative 5. Negative 9 plus a negative 5 is a negative 14. Finally, the last one here is row 3, column 3. So still using row 3 of the first matrix. Now on to column 3 of the second matrix. The first element is 3 times 2. Plus the second element, negative 1 times negative 2. 3 times 2 is 6. Negative 1 times negative 2 is 2. 6 plus 2 makes 8. So that is our matrix. 17, 0, 4, negative 8, 6, negative 4, 13, negative 14, and 8. That is the result of that matrix multiplication. I realize it's a long process, but it's okay. It'll get worse, trust me. So our next step, I want to talk about identities. Every operation we have done so far has something called an identity element. For addition, that identity element was 0. I can take any number A, if I add 0 to it, I still have A. For multiplication, that identity element was 1. I can take any number, let's call it B. If I multiply it by 1, it's still B. For matrices, the identity element is a diagonal matrix. So a diagonal matrix is always, of course, square. So a diagonal matrix has ones along the diagonals, and zeros everywhere else. So this is a 2 by 2 diagonal matrix. A 3 by 3 diagonal matrix, of course, is just going to be like that. 1, 0, 0, 0, 1, 0, and 0, 0, 1. If I multiply a matrix, any matrix, by an identity element, I will get back the matrix I started with. For example, let's take 5, 3, 7, 4, negative 2, 1. First thing I need to decide is what size identity matrix I need, or what size diagonal matrix I need. This is a 3 by 2 matrix. Remember, it's the columns of the first matrix have to line up with the rows of the second matrix. So that second matrix, the identity matrix, has to be a 2 by 2. So it's going to be the 1, 0, 0, 1 is what I'm going to multiply by. So in my result is going to be a 3 by 2 matrix. 3 by 2. In my first location here, row 1, column 1, you'll notice I have 5 times 1. The 0 isn't going to do anything. Row 1, column 2, well, I've got 5 times 0 and 3 times 1. So that's just 3 times 1, which is 3. In row 2, column 1, I got 7 times 1 and 4 times 0. That's just the 7. Row 2, column 2, I got 7 times 0 and 4 times 1. That's just the 4. Row 3, column 1, so row 3 times column 1, I've got negative 2 times 1 and 1 times 0. That just gives me the negative 2. And finally, row 3, column 2, negative 2 times 0 is 0, 1 times 1 is 1. So it just gives me the 1. Note, that gave me back the same matrix I started with. That's called the identity matrix. Let's talk about inverses. Inverses in our other operations got us back to what we started with, undid what we had done. A number times its inverse element gives us back the identity element. So for addition, the inverse was the opposite of the number. If I add negative a, I get 0. Note that 0 was the identity element for addition. Negative a, or opposite a, is the inverse of a. For multiplication, if I have b, it's going to be times the reciprocal of b, 1 over b, gives me 1. Note that 1 was the identity element for multiplication. The reciprocal is the inverse, the multiplicative inverse of b, 1 over b. So for matrices, the inverse of a matrix if I have matrix M times its inverse, that M with a little negative 1 by it, that means the inverse of M. When I multiply those, I better get the appropriate identity matrix. So 1, 0, 0, 0, that diagonal matrix of the appropriate size. Now, only square matrices. Remember, square means the number of rows equals the number of columns. Have inverses. So the question is, how do we find the inverse? Well, let's say I have a matrix. I'm going to start out with a simple 2 by 2. Two, negative 1, 3, 5. And I want to find its inverse. Well, I am just going to create its inverse. I'm going to just go A, B, C, D are the elements of that inverse. I know this has to multiply to give me a 2 by 2 diagonal identity matrix. So 1, 0, 0, 1. It's break time, so when we come back from break, we will look at how we solve that. So let's go ahead and take 10 minutes. We'll be back at 10. So we left off before break with this example that if this is our matrix M, this is assumed to be the inverse of that matrix M, they must multiply to make that diagonal identity matrix. So let's look at the elements here. Now, the only elements that have values here are those diagonals, but the other ones count too. We'll have to look at those as well. But for row 1, column 1, we use row 1 of the first matrix, column 1 of our second matrix. So that is telling us that 2A plus, well, minus negative 1C, or just minus C, has to equal 1. We move over to the next element, the 0 there, that's row 1, column 2. That tells us that 2B plus negative 1Z, or just minus D, has to equal 0. Moving then to the next one, row 2. So that'll be row 2 of the first matrix. Column 1, so that'll be column 1 of the second matrix. So 3 times A plus 5 times C has to add up to 0. And then our final element here, row 2, column 2. So it's still row 2 of the first matrix. Now it's column 2 of the second. We have 3 times B plus 5 times D has to equal 1. So this system of equations here must be true. So I've got 2, 0 for B, -1 for C, 0 for D, augmented with a 1. 0 for A, 2 for B, 0 for C, -1 for D, augmented with a 0. 3 for A, 0 for B, 5 for C, 0 for D, augmented with a 0. 0 for A, 3 for B, 0 for C, and 5 for D, augmented with a 1. So this matrix here can be solved to find A, B, C, and D. Let's go ahead and do our Gaussian Jordan elimination to solve this. We already have a lot of zeros. All we have to do is get these 4 elements to be zeros and then make it ones down the diagonal, which we can always just divide once we have, once the diagonal is the only value, we can just divide the row to make that a 1. So let's look at, I'm going to combine row 1 with column 3. Not necessarily in the way you might expect me to. I'm going to take row 1 times 5, which will give me 10, 0, -5, 0, augmented with a 5. Row 2 we're going to leave alone. Actually, you know what? While we're at it, let's do row 2 with a 5 as well. We're going to combine some operations here. Row 2, I'm also going to multiply by a 5. So give me 0, 10, 0, -5, 0. Rows 3 and 4, we're going to leave alone. Now, I'm going to do some combining here. Row 1, I'm going to leave in its original form what we had before up here. The 2, 0, -1, 0, and 1. Row 2, I'm going to leave in its original form. 0, 2, 0, -1, and 0. Row 3, I'm going to combine this modified row 1 with row 3. I'm going to add those to get a new row 3. So I've got 10 and 3 makes 13. 0 and 0 is 0. -5 and 5 is 0. 0 and 0 is 0. 5 and 0 is 5. For row 4, I'm going to combine my modified row 2 with my row 4. I'm going to add those to get my new row 4. So I have 0 and 0 is 0. 10 and 3 is 13. 0 and 0 is 0. -5 and 5 is 0. And 0 and 1 is 1. So now I'm going to do some rearranging. I'm going to rearrange my order here. I'm going to put this row first. 13, 0, 0, augmented with a 5. This row second. 0, 13, 0, 0, augmented with a 1. This row is going to go third. 2, 0, -1, 0, augmented with a 1. And this row goes last. 0, 2, 0, -1, 0. And my first 2 rows are now pretty much complete. I'm going to divide out 13 in each of them. Now we get some kind of ugly numbers here, but that's okay. So 13 divided by 13 is 1. Well, 0 divided by 13 is 0 no matter what. 5 divided by 13 is 5/13. The next row, again, 0 divided by 13 is 0. 13 divided by 13 is 1. Then we got zeros. 1 divided by 13 is 1/13. I'm going to do nothing with those bottom two rows right now. Actually, you know what? I am going to do something with them. I'm going to multiply both of those by a -1. So this will be a -2, 0, +1, 0, -1. This will be a 0, -2, 0, +1, 0. We will see we're getting really close. We have all zeros up here to the upper right. We have all ones on my diagonal. All I have to do is in the lower left here, get rid of those two numbers. So I'm going to start out, I'm going to take the top row times 2. That'll give me 2, 0, 0, 0, augmented with 10/13. I'm going to actually take the second row times 2 as well. Give me 0, 2, 0, 0, 1/13 times 2 is 2/13. And the last rows I'm going to leave as they are. So -2, 0, 1, 0, -1, 0, -2, 0, 1, 0. So for my top rows, I'm going to leave them as they were. 1, 0, 0, 0, 5/13. 0, 1, 0, 0, 1/13. For my third row, I am going to combine my modified top row with my third row to replace the third row. 2 and -2 is 0. 0 and 0 is 0. 0 and 1 is 1. 0 and 0 is 0. 10/13 and -1 is a -3/13. And then for the bottom row, I'm going to take my modified second row, combine it with the bottom row to replace the bottom row. So I have 0 and 0 is 0. 2 and -2 is 0. 0 and 0 is 0. 0 and 1 is 1. 2/13 and 0 is 2/13. So what this tells me, top row says A is 5/13. Second row says B is 1/13. One disappeared there. Third row is telling me C is -3/13. And the fourth row is telling me D is 2/13, which is saying that the inverse of this matrix, 2, -1, 3, 5, if that is M, the inverse of M is 5/13, 1/13, -3/13, and 2/13. If I do multiply those together, we do find that we get that diagonal matrix, 1, 0, 0, 1. Now that's not an easy set of calculations to do by any means. And then if this is a 3 by 3 matrix, well, it gets even worse because we end up dealing with well, we end up having 9 variables instead of just 4 that we have to work with. That's no fun at all. There is one other way of finding an inverse. the alternative method for finding an inverse. I take my matrix, so I had, what was the matrix I had? Scroll back up here. 2, negative 1, 3, 5. To find its inverse, I create a matrix, 2, negative 1, 3, 5. And I'm going to augment that matrix, not with just a single column, but now with a column of several columns that contain my diagonal matrix. Now what I am going to do is I am going to use Gaussian Jordan elimination to make this matrix a diagonal matrix. Whatever the result is over here will be the inverse. So looking at this, I'm going to start out by taking my first row times 5. I've got 10, negative 5, 5, 0. I am going to combine that with the second row. Well, there's really only 2 rows to combine. I'm going to replace the first row with that. So I've got 10 and 3 makes 13. Negative 5 and 5 is 0. 5 and 0 is 5. 0 and 1 is 1. So I've got 13, 0, 5, 1. Bottom, I still have 3, 5, 0, 1. I am going to divide that top matrix by 13 because I wanted that element to be a 1 there. So I divide by 13. That becomes a 1. 0 divided by 13 is 0. 5 divided by 13 is 5/13. 1 divided by 13 is 1/13. Not going to do anything with that second row yet. I'm going to multiply this top row by a negative 3. That's going to give me negative 3, 0, augmented with a negative 15/13 and a negative 3/13. My bottom row is not going to change right now. So I'm going to combine those 2 rows and replace the bottom row. So the top row is going back to what it was, 1, 0, 5/13, 1/13. The bottom row is going to be from combining those. Negative 3 and 3 is 0. 0 and 5 is 5. Negative 15/13 and 0 is a negative 15/13. Negative 13/13 and 1 is 10/13. So the last thing I have to do is divide this second row by 5 to make this a 1. So my top row stays the same. My bottom row, 0 divided by 5 is 0. 5 divided by 5 is 1. Negative 15/13 divided by 5 is a negative 3/13. 10/13 divided by 5 is a 2/13. That is exactly the inverse matrix we came up with before. I'm going to let you guys try one in your notes. So I'm going to call this matrix A. I ask you to find A inverse. I'm going to give you a few minutes to work on that. Use whichever method you prefer. Let's take a look and see if you're going the right route here. I'm going to do this. I prefer to use the parallel matrix method here, where I augment the matrix with that identity matrix. And I'll notice that bottom row already has a 0 in the first column, which is what I want. So I'm going to go ahead and finish off that bottom row by dividing it by 3. So that top row isn't going to change right now. 4, 2, 1, 0. The bottom row becomes 0, 1, 0, 1/3. The bottom row is now done, but we have to use it to finish the top row. So I'm going to multiply the bottom row by -2. You get 0, -2, 0, -2/3. The top row is going to stay the same. Now I'm going to add those two rows together and I'm going to replace the top row with it. 4 plus 0 is 4. 2 plus -2 is 0. 1 plus 0 is 1. 0 plus -2/3 is -2/3. For the bottom row, I'm going to go back to what it was before I multiplied it. 0, 1, 0, 1/3. My last step here is just take that top row and divide it by 4. So 4 divided by 4 is 1. 0 divided by 4 is 0. 1 divided by 4 is 1/4. -2/3 divided by 4 is -1/6. In the bottom, I got 0, 1, 0, 1/3. So the inverse matrix, if matrix A is 4, 2, 0, 3, as we had, A inverse is 1/4, -1/6, 0, 1/3. Okay, so an application of this. One application of this is in encoding encryption. There's a couple of variations of it. The most common variation is to use a 3x3 matrix. And then we use a key matrix to encode it and the inverse of that matrix to decode it. But 3x3 matrices are a little tough. We really don't want to go through the effort of, at this point, we don't want to go through the effort of finding the inverse of a 3x3 matrix. It's a lot of work. You could use that parallel matrix method like we just used. It's just a lot of different steps to do it. So and this allows us to use words. If we use the 3x3, this will allow us to use up to 9-letter words because there are 9 spaces in it. We're going to look at a simplified version. We're going to go up to 4-letter words. Four letters is because we're going to just use a simple 2x2 matrix. And to encode this, we're going to use the letters of the alphabet. A, B, C, D, E, F, G, we'll stop at T. We don't necessarily need to to go any further. And we're just going to number them 1 through 26. So if I want to encode, let's say I want to encode a 3-letter word like the. T is 20, H is 8, and E is 5. I would put that in the matrix, 28, 5, and 0 indicates that there wasn't a 4th letter in that word. Now I am going to pick a random matrix, but a random invertible matrix. So the invertible matrix might be 4, 10, 2, 6. And I'm going to use that matrix to encode this. I do it by multiplying the word matrix by my encoding matrix. So in my matrix here, I've got 20 times 4 is 80, plus 8 times 2 is 16. So my first entry is a 96. My second entry, 20 times 10 is 200, plus 8 times 6 is 48. So 248. My third entry, I've got 5 times 4 is 20, plus 0 times 2 is 0, just a 20. And my fourth entry, I've got 5 times 10 is 50, plus 0 times 6 is 0, so that's just a 50. So that's my matrix, my encoded matrix for that word. 96, 248, 20, and 50. That's the word the encoded with that key. Now to decode it, I have to invert this matrix. So I'm going to do oops. You may be getting an alert across your screen right now. I'm going to pause here. So I'm going to take the bottom row and multiply it by a -2. So we got -4, -12, 0, -2. And now I'm going to combine it with the top row. So the top row I'm going to leave as it is for now. I'm going to combine those and replace the bottom row. So I got 0, -2, 1, -2. Bottom row now, I'm going to divide out that -2. So that bottom row is 0, 1, -1/2, 1. Top row, I'm not going to change quite yet. Actually, you know what? I can do one thing with that top row. I'm going to divide that top row by 2, just to simplify it a little bit. So give me 2, 5, 1/2, and 0. Now I can multiply my bottom row by a -5. So the top row isn't going to change. 2, 5, 1/2, and 0. Should spread things out a little bit more there. Bottom row is 0, -5, +5 halves, -5. I'm going to combine those two rows to replace the top row. So I've got 2 plus 0 is 2. 5 plus negative 5 is 0. 1/2 plus 5/2 is 3. 0 plus negative 5 is negative 5. On bottom, I'm going to go back to what that was before, 0, 1, negative 1/2, and 1. Top row is going to get divided by 2. So that top row is going to become 1, 0, 3/2 or 1.5, negative 5/2 or negative 2.5. Bottom row stays 1, 0, negative 1/2, 1. So that is my inverse. 1.5, negative 2.5, negative 1/2, and 1. That is my decoding key. So I take my coded matrix, 96, 248, 20, and 50. And I'm going to decode it by multiplying by this inverse of my code matrix. So 1.5, negative 2.5, negative 1/2, and 1. Now I made this example up on the fly, so hopefully this works out on the first try. So our first element here is going to be 96 times 1.5. That's 144. Plus the 248 times negative 1/2 is a negative 124. That adds to make 20. Second element, 96 times negative 2.5 is negative 240. 248 times 1 is a positive 248. That adds to make 8. Next, we have row 2, column 1. 20 times 1.5 is 30. 50 times negative 1/2 is negative 25. That adds to make 5. Then we got row 2, column 2. 20 times negative 2.5 is negative 50. 50 times 1 is a positive 50. That adds to make 0. So we get 2850. 20 was T, 8 was H, 5 was E. So we do get back to our original word. Now, 2 by 2, again, we're limited to only 4-letter words or less. 3 by 3 allows us to go up to 9-letter words, which is pretty much, you can make a pretty significant message if you're allowed up to 9-letter words. Trying to guess a 2 by 2 matrix is a 1 in 10,000. A 3 by 3 matrix, trying to guess that matrix to decode it, is a 1 in a billion shot. So you can see it's a fairly effective coding tool. Now, before we call it a day, I want to take time to make sure you guys know what is on our second midterm test coming up on Monday. So first of all, you've got the old homework from last week. I believe that is homework 9B. It is due tomorrow. It's due Thursday. Then you have a quiz. Quiz 9 that'll be due Friday. And you do still have homework from today, homework 10A, which will be due next week, Tuesday. And there is a test 2 review that is out in my math lab, along with the others. That is extra credit. And I believe I have that set to be due next Wednesday for you. Just like before, that's up to 20 points for how you do on that review. For test 2 coming up. Our topics that you will need to make sure you remember how to do. Solve logarithmic and exponential equations. So using a log to undo an exponential or using an exponential to undo a log. You need to be able to solve systems of equations. Whether those are 2-variable, 3-variable, or nonlinear. You need to be able to solve systems of inequalities. Of course, systems of inequalities are going to have to be on a graph. You are going to need to be able to use matrices to do basic matrix operations, to find inverses like we did today, and to solve systems of equations. You can use either the Gaussian elimination with back substitution, or you can use the Gaussian Jordan elimination. You'll need to be able to do a partial fraction decomposition. For breaking that more complex equation into a partial fraction, you may have to factor the denominator yourself. Be prepared for that. You'll need to be able to use your rules of logarithms to expand logs or to combine logs or to calculate a log using change of base formula. There isn't a log base 7 button on your calculator, so how do you do a log base 7? And then you need to be able to do applications of logs using formulas for growth or decay. Graphing. You need to be able to graph a system of inequalities. You'll need to be able to graph an exponential function. You need to be able to graph a logarithmic function. Going back way to the beginning, actually, I'm not going to make you graph polynomial functions and rational functions, but you will need to be able to do linear programming to maximize or minimize an objective function. You need to be able to solve rational inequalities, and polynomial inequalities. This goes back to our first day of Unit 2. And then I will offer extra credit right on the test for this one, as far as some questions that I wouldn't expect you to necessarily be able to solve, but definitely if you're able to solve them, they're worth extra credit. It might be systems of equations involving fractions or some complex exponential or logarithmic equations that I'll throw on there. But those, again, are by no means expected. They're just out there as an extra opportunity. If I tried to be a lot nicer on this test, I realized was doing the key for test 1 that I was really kind of cruel on that one. So I tried to be a little kinder to you, not quite so mean. So hopefully, as you're taking this test, you will have a little bit of time left over for extra credit. Anybody have any questions on the test or on the new material for today? Okay, well, you guys have a great day. We will see you on Monday. If you would like to start the test early on Monday, I will have it sent out by the end of the day Friday. At each of your locations, you just have to go to the library, and the ITV staff are also the library staff at your locations. So if you just go to the library and ask them for the test so you can start early, that's okay. I will make note on there when I send it out that it's okay to start early and okay to work in the library in a private room if you need to until class starts or after class starts if you prefer to stay there. Okay, so we'll see you guys on Monday.